Okay, today I'd like to do one of my favorite problems. And this problem is about a loop of wire. And the loop of wire is in a region of a magnetic field. Maybe there's a big magnet. But the magnetic field, these X's here, mean that the magnetic field points into the page. Okay, and the question is, how much force do you have to provide to get the loop to move into the region of field at some constant speed v? Now, we should figure out why we have to apply some force anyway, and that's going to be important for solving this problem. Okay, so why do we have to apply force? The reason why we have to apply force is that as the loop is heading into the region of the magnetic field, the flux is increasing. The flux is increasing. Okay, so what does that mean? Well, what that means is that the amount of area with magnetic field going through it is increasing. And Faraday found that when the magnetic flux is increasing, there's an EMF, there's essentially a voltage being induced in the wire. So that means that a current flows in the wire. And now we have a current in a magnetic field. Well, we know that a current in a magnetic field feels a force. And so it's in fact that force that we have to counteract. Pretty cool, huh? Okay, so let's see if we can kind of tease this out. Let's say that the distance is A and B, the size of the loop. Let's make this a square loop just to be a little bit easier. And the magnetic field has some strength B. Well, now we can write that the magnetic flux is just that magnetic field, B, times the area. And, well, gosh, I don't really have the area here that's in the magnetic field, so I'll define a new variable here, y. But keeping in mind that I've just made that part up, and that's going to be changing. But we'll continue on and see what happens with that new variable. Okay, so we have the amount that's actually in the magnetic field, that's this part. That is y times A. Oh, here's the cool part. The cool part is that if this is the flux is changing. The flux is increasing. So the rate of change, here we go. The rate of change of the flux is, well, the B doesn't change, and the A doesn't change, the width of the loop, but the amount that's actually in the loop, that part is changing. So taking that derivative is pretty simple, because now it's just the part that's in the magnetic field, and the rate that this variable is changing, that was actually given. That was given as the speed v. Okay, so we'll write this as b, a, v. That's the rate of change of the flux. So what Faraday said is Faraday said that the voltage, the EMF that's induced, is equal to this. So Faraday said that this is the voltage induced in the loop. So that means that the current, well, that's just Ohm's empirical relationship. So V equals IR is how most of us remember it. So I'm thinking here that V is IR. But what we need here is that I is V over R. And so the voltage that's induced is B, A, V. And then we divide by the resistance. So now what we need is we need the force that is induced, or rather the force that is required to move the loop at that speed v into a region of magnetic field. Okay, let's see. So I want the relationships that says the force is I, L cross B. And so I have the current. L in this case, remember, the L goes with the I. So it means the length that the current is traveling through. Well, hang on now. We should think about this for a second before we proceed. Because, here's the aside, we notice that if there's current running around this loop, all four of these sides are going to experience a force that we would potentially have to counteract. The two sides, however, do not have a net force because those forces balance out. The one at the top, because that's not actually in the magnetic field at all, that doesn't have a force. It's only this one down at the bottom that actually is the force we're trying to counteract. That's the only thing that gives it a net force. And while we're on this topic, actually, we should check to see what direction the force is. So what we're going to do is we're going to use the right-hand rule here. And we know from Lenz's law says that the current induced creates a flux opposite to the change that created it. Okay, so let's see. If the flux is going into the page, that means that this current creates a magnetic field out of the page. So let me show you what my hand is doing here. Basically, my hand is saying if I want my fingers, here's my fingers. If I want my fingers to curl out of the page, there's my right hand, okay, then this means that the current has to go in the direction of my thumb. And I'll actually, just to be on the safe side, curl my fingers around the bottom so that they are pointing out inside the loop. Not outside, inside the loop. And once again, well, it's not a very good drawing of a hand, but once again, my thumb points to the right. So the current goes this way. Whoop, not that way. There we go. Has to be consistent. Goes that way, which is counterclockwise. So, well, what I drew previously, I just got lucky. Now that I've checked, I can say for sure that this is counterclockwise. Okay. So it's this piece down here that feels the force. Now, it's not the force due to the field it creates, that's not right, but due to the field that it's already in. So what we have here is we have a current going this way and a magnetic field going this way. So once again, we'll do the right-hand rule, and we find that the current going this way and into the field going into the board, the force that B field creates, force that B field creates on the current goes up. And that makes sense because to counteract, we have to push downward. Okay, back to the story at hand. So we said that force is equal to I, and the L is just this length down here, which was called A, times that B field. And I can now substitute in what I had for the current. I already got that part from before. I had B, A, V over R, okay, times A times B, which is, I'll put some things together here, B squared, A squared, V divided by R. And that's the answer. But wait, there's more. This is the coolest part. So now you're pushing with some force, right? You're pushing with some force, and because you're pushing, you're getting a current to flow. And the power that you have to provide is the force times some velocity. That's the power that you provide. So that's B squared, A squared, V squared over R. But check it out now. The power that's simply dissipated by a resistor And if R is the resistance in the wire, dissipated by a resistor, because you are pushing, we know that the power dissipated is the current times the voltage. Well, let's see. The current was BAV over R, right? We had that from before. And the voltage was the EMF that was induced from the previous page, so that's BAV. Check it out. The power that the resistor dissipates, B squared, A squared, V squared, all over R, holy smokes, that's the same thing as the power that you have to apply. But that makes sense. You don't get something for nothing. And the power that you apply, well, that came from your Wheaties. It came from your breakfast this morning. And that power is exactly the power then dissipated by the current now flowing in the wire. This is one of my all-time favorite problems. Enjoy!